Uranus, the most mysterious ice giant in the solar system. Among the planets of our solar system, Uranus stands out as a celestial anomaly, an enigma wrapped in shimmering blue clouds, marked by a series of baffling scientific phenomena that continue to elude full understanding. Unlike other planets, Uranus has only been visited once by a spacecraft, NASA's Voyager 2, which conducted a brief flyby in 1986. Despite the limitations of that single encounter, the mission returned data that even today forms the foundation of our knowledge about this distant world. Since then, astronomers and planetary scientists have relied on remote observations and advanced simulations to piece together the mysteries surrounding this ice giant, a planet that orbits on its side. Uranus's most striking feature is its extreme axial tilt. The planet is tipped over at an angle of nearly 98 degrees, effectively rotating on its side compared to the other planets. This bizarre orientation causes extreme seasonal variations and poses a significant puzzle. What event caused this radical tilt? Most experts believe that Uranus was knocked onto its side by a massive impact with a protoplanet, possibly twice the size of Earth, some 4 billion years ago. This ancient collision may have also shaped several of Uranus's other defining features, including its strange internal heat distribution and magnetic field. A magnetic field unlike any other. Unlike Earth's well-aligned dipolar magnetic field, characterized by a north and south magnetic pole, Uranus's magnetic field is wildly asymmetric and multipolar. In fact, it possesses not just 2, but 4 magnetic poles. This field is tilted 59 degrees from the planet's rotational axis and offset from the planetary center by nearly a third of the planet's radius. Originally discovered by Voyager 2, this configuration defied conventional geodynamo models, which typically involve convective motion in a planet's liquid metal core. Earth's field, for example, is generated by convection in its molten outer core surrounding a solid iron center. But Uranus, lacking the necessary internal structure and dynamics for a similar dipolar field, hinted at something much stranger: the chilling mystery of Uranus's coldness. Another confounding aspect of Uranus is its temperature, or rather, its lack thereof. Despite not being the farthest planet from the Sun, Uranus is the coldest, with atmospheric temperatures plunging to a frigid minus 224 degrees Celsius minus 371 degrees Fahrenheit. The reason for this unexpected chill is not fully understood. Scientists suspect that the aforementioned ancient collision may have caused the planet to lose much of its primordial heat or trapped it beneath insulating layers of ice in the mantle, hindering its escape into space. Voyager 2's surprise encounter. During its flyby, Voyager 2 recorded a surprisingly intense radiation belt surrounding Uranus. These belts were found to be filled with high-energy, fast-moving electrons, comparable in strength to Jupiter's mighty radiation belts. Yet, unlike Jupiter, Uranus appeared to lack the plasma sources, such as volcanic moons, that could supply the electrons. For decades, this contradiction puzzled scientists. But a recent breakthrough has finally provided a plausible explanation. A team led by Jamie Jinksey at NASA's Jet Propulsion Laboratory re-examined the original Voyager 2 data with fresh eyes. They discovered that the probe had encountered Uranus during the aftermath of a major solar storm, which had dramatically compressed the planet's magnetic field. This storm stripped away surrounding plasma, while simultaneously flooding the radiation belts with solar electrons. In essence, Voyager 2 had observed Uranus in an exceptionally rare and turbulent state that misrepresented its normal magnetospheric conditions. Statistically, such a situation might only occur about 4% of the time, making Voyager 2's timing both unfortunate and scientifically serendipitous. Rain of diamonds and exotic matter. The strange internal behavior of Uranus has long prompted speculation. One hypothesis posits that under immense pressure deep within the planet, hydrocarbons break down and compress into diamonds, potentially forming diamond rain. These falling diamonds could, in turn, generate heat and convection currents within the mantle, contributing to the magnetic field. Other theories suggest the presence of exotic forms of matter, such as superionic water. In this state, water molecules arrange themselves so that the oxygen atoms form a solid lattice, while hydrogen ions move freely, allowing the substance to conduct electricity. This superionic layer could serve as a conductive zone powering the magnetic field. New research, layered interiors and magnetic fields. Recently, a novel explanation has emerged, thanks to Professor Burkhard Militzer from the University of California, Berkeley. Using high-resolution, atomically precise simulations, Militzer's team examined the behavior of methane, water, and ammonia under Uranus-like pressures and temperatures. The results were surprising. The substances separated into immiscible layers, much like oil and water. At the outermost interior lies a thick, conductive layer of water and ammonia, about 8,000 kilometers deep, where convection likely occurs. Beneath it, however, lies a stable, stratified zone rich in nitrogen-bearing hydrocarbons. These layers become denser with depth and do not mix vertically, effectively blocking deeper convection. This structure explains the multipolar magnetic field. Only the upper convective layer contributes to field generation, leading to a complex, offset configuration. A new moon and the growing Uranian family. In addition to these magnetic revelations, Uranus's satellite family has grown. Recently, astronomers discovered a new moon, temporarily named S/2023U1, increasing the planet's known moons to 28. Measuring just 8 kilometers across, it's the smallest Uranian moon discovered to date. Each new discovery in the Uranian system provides a small but vital piece of the puzzle, offering insights into the planet's formation and evolution. The future of Uranus exploration. Despite all these exciting findings, one frustrating reality remains. No dedicated mission to Uranus is currently in development. Several proposals, such as ESA's Uranus and Neptune twin probe concept, exist on paper, but none have yet moved beyond the conceptual stage. A dedicated orbiter or atmospheric probe could revolutionize our understanding, providing critical data on the planet's internal structure, atmospheric composition, magnetic field dynamics, and moons. Conclusion: a planet of unanswered questions. Uranus continues to baffle and amaze scientists with its unique characteristics, from its sideways spin and cryptic magnetic field to its bitter cold and layered interior. Each new finding raises more questions, reminding us how much we still have to learn about the outer reaches of our solar system. Until a new mission ventures into the icy depths of Uranus, many of its secrets will remain frozen in time, waiting for the next generation of explorers to uncover them.